This week we've been looking at the bivariate regression model, and in this video I'm going to concentrate on the material from lecture 4 in which we introduced the bivariate regression model and we developed estimators of the intercepts and the slope coefficients. We also went on to show that under the Gauss-Markov assumptions the slope coefficient is unbiased. This week we've been looking at the least squares regression model. In the first stage we've been developing the estimates of the intercept and slope parameters, and we obtain these by taking the residual sum of squares function and then finding the first order conditions for a minimum of the residual sum of squares. So we differentiate with respect to alpha hat and beta hat, and then we use these first order conditions to solve for the unknown parameters. In the first stage we show that we can obtain what we call the least squares normal equations from these first order conditions. This is essentially a pair of simultaneous equations in alpha hat and beta hat which we can solve for our estimates. Least squares normal equations lead to some quite interesting results. First of all, if we take the first of the least squares normal equations here, we see that dividing through by n, the number of observations, we can show that the regression line must pass through the sample means of the data. So we have y bar equals alpha hat plus beta hat x bar. Now we can go on to use that to develop our estimator of the slope coefficient. First of all, if we solve for alpha hat, we have alpha hat equals y bar minus beta hat x bar, and then we substitute that into the second of the least squares normal equations here. And this gives us the equation here. Now if we group together the terms in beta hat on the left hand side and the other terms on the right hand side, then we obtain this equation here. Beta hat into sum of xi squared minus nx bar squared equals sum of xy minus n x bar y bar. But we can write that in a more convenient form. First of all, we note that the sum of xi squared minus n x bar squared equals the sum of xi minus x bar all squared. This is a very easy thing to demonstrate using algebra, so I'll leave that as an exercise. Secondly, we can show that the sum of xi yi minus n x bar y bar equals the sum of xi minus x bar yi minus y bar. Again, this is left as an exercise. So we can write our expression for beta hat in the form given here. We have beta hat multiplied by the sum of xi minus x bar squared equals the sum of xi minus x bar yi minus y bar. And if we divide both sides by sum of xi minus x bar squared, we have the expression that we use for beta hat. But there's one other interesting feature of this. If we divide both numerator and denominator of this expression by the number of observations n, then we can see that what we obtain is on the numerator the sample covariance of x and y, and on the denominator the sample variance of x. So we can interpret the slope coefficient of our regression equation as being the ratio of the sample covariance of x and y to the sample variance of x. Now it's worth thinking a little bit about what these parameters are telling us. If we take a quick look at the graph of the scatter diagram, then we see that what we're doing effectively here is we're fitting a line through a scatter of points to try and minimise the sum of the squared vertical distances between the scatter of points and the line. And the way we're choosing our parameters is first of all to set the slope equal to the ratio of the covariance of x and y to the variance of x, and then the intercept is set such that the regression line passes through the sample means of the data. So there's one point here, y bar x bar, corresponding to the sample means, and that regression line must pass through that point. The next stage is we want to go on to say something about the nature of the parameters we've estimated. What I want to do first of all is to concentrate on the slope coefficient. And what we're going to do is to show that the slope coefficient is unbiased in the sense that the expected value of the slope coefficient, our estimate of the slope coefficient, equals the true value. So how do we go about doing that? Well, to do that we need to use the Gauss-Markov assumptions that we covered in the lecture. But first of all, let's just write down our regression model. We've got y equals alpha plus beta xi plus ui, and we have our estimate of beta hat equals sum of xi minus x bar, yi minus y bar, of the sum of xi minus x bar squared. Now it's easier to work with a regression in mean deviation form rather than having the intercept in. So first of all, let's note that if we take averages, then the average of y bar equals alpha plus beta x bar plus u bar, the average of the random errors. That's just a matter of simple arithmetic. And if we subtract that from both sides of this equation here, then we can eliminate the intercept term. We'll get yi minus y bar equals beta xi minus x bar plus ui minus u bar. Now we can substitute the yi minus y bar into our expression for beta hat and then use that to say something about the estimates. So if we have beta hat equals sum of xi minus x bar multiplied by this expression here, which is the yi minus y bar, all divided by sum of xi minus x bar squared. Now again, this is just a matter of arithmetic. If we multiply this expression out, we'll see that the first part of it here will have sum of xi minus x bar squared times beta over the sum of xi minus x bar squared, and those will cancel, leaving us just with a beta term here. Then if we multiply the rest of the expression, we'll have, as here, sum of xi minus x bar, ui minus u bar over the sum of xi minus x bar squared. Now again, we can do a little bit more than that. If we multiply this second part out, we separate the ui and the u bar terms, we have the expression that's given here, beta hat equals etc. And we note that the second bit of this, minus u bar sum of xi minus x bar over sum of xi minus x bar squared, must be equal to 0. Why is that? Well, we've got the sum of xi minus x bar here, and that's equivalent to the sum of xi minus n times x bar. But the definition of x bar is sum of xi over n, so this must cancel, this must be 0. So we can effectively ignore the term in u bar here, just concentrate on these first two bits here. Now what we're interested in doing is showing that the least squares slope coefficient estimate is unbiased if the Gauss-Markov conditions hold. And in particular, we want to ask which of the Gauss-Markov conditions are crucial to showing unbiasedness. So if we take expectations through this expression here, we can write it as the expected value of beta hat equals beta, and then using Gauss-Markov assumption 4 that the x's are non-stochastic, we can take the x's outside the expectations operator and write to the second bit as the sum of xi minus x bar expected value of ui divided by sum of xi minus x bar all squared. Now remember, the first of the Gauss-Markov assumptions is that the expected value of ui is equal to 0 for all values of I, and therefore it follows that if that assumption holds, as well as Gauss-Markov 4, then the expected value of beta hat equals a true value beta, i.e. beta is unbiased. Now what's interesting here is to note which of the Gauss-Markov assumptions we needed to use in order to prove unbiasedness. We've only actually used two. We've used the fourth assumption that the x's are non-stochastic. This enabled us to take the x's outside the expectations operator, and we've used the first Gauss-Markov assumption that the expected value of ui was equal to 0. We've not used assumptions 2 and 3. So what this suggests to us is that assumptions 2 and 3 are not crucial to proving unbiasedness. And indeed what we'll find is that we can have serial correlation or heteroscedasticity and we'll still have an unbiased estimate.